For generations, we as a human race have been obsessed with dyeing. All sorts of colors, all sorts of things to dye. And the craze never stopped. So I decided to have a little fun of my own, and to try some dyeing of my own, and then to see what effects it had on the fabric.
Work it, make it, do it, makes us harder, better, faster, stronger. More than power, power, never, ever, after work is over. Work it, make it, do it, makes us harder, better, faster, stronger. Work it harder, make it better, do it faster, makes us stronger. More than ever, hour after hour, work is never over. Work it harder, make it better, do it faster, makes us stronger. More than ever, hour after hour, work is never over. Work it harder.
So, what just happened? Let's take a look at some of the chemistry behind dyeing. Before we begin, let's make a quick definition of what a dye actually is. We will expand upon this later, but for now, let's call a dye a substance that is dissolved or dispersed in a solvent and then applied to a substrate or fiber that it has an affinity for. The solvent is typically water. Next, let's understand why a dye makes a substrate colored. Better yet, let's discuss what colored means. When you say something looks colored, you're basically saying that it either reflects or absorbs electromagnetic radiation in a narrow region called the visible spectrum. As the name implies, this is a spectrum of light that humans can actually see. What happens with color in liquids and solids is this. White light hits the liquid or solid, and the liquid or solid either absorbs or reflects colored wavelengths of light. Interestingly, the color that the liquid or solid absorbed is not necessarily the color that we actually see. Take a look at these diagrams here for visual aid. In the first one, white light hits the solid, and the solid absorbs green from the white light and then reflects purple to our eyes. In the second one, white light hits the liquid, and the liquid absorbs blue and appears yellow. Check out this table that shows different wavelengths and corresponding colors. So what causes these solids and liquids to interact with white light in these ways and appear colored? Well, a couple of different things, such as molecular excitation resulting from rotation/vibration of molecules, distortion of d-electron shell caused by ligands surrounding the ion. This happens only with transition metal complexes. Electronic motion in conjugated organic systems and charge transfer. The band theory, which is the blurring of many orbitals throughout crystalline solids. Solids are only colored if the gap between the highest occupied molecular orbital and the lowest unoccupied orbital is small enough. And the refraction, scattering, dispersion, and diffraction of color due to geometrical and physical dimensions. So, which of these reasons for color applies to dyes? Typically, dye molecules are organic conjugated systems. The color in dyes comes from overlapping p orbitals, which causes all electrons to absorb energy equally. Conjugated organic molecules absorb specific wavelengths of electromagnetic radiation. If the absorption is within the visible spectrum, light reflected or transmitted is deficient in a particular color, and the solid or liquid the dye is in appears colored. The hue of the dye depends on the wavelength it absorbs. The length of the wavelength a dye can absorb depends on its structure. Therefore, any change in the P system will affect the hue. A structural change which causes the absorption band to longer wavelengths is called a bathochromic shift. The opposite, going to shorter wavelengths and warmer colors, is called a hypostochromic effect. Now that we understand color better, let's look at an actual dye molecule. A dye molecule can be separated into two parts, the chromophore and the oxochrome. The chromophore is a group of atoms which controls the color of the dye and is usually electron withdrawing. Oxochromes are normally electron donating. The two groups are connected by a conjugated system. Different types of dyes will have different types of structures, but all have the same basic one. Let's look at the general structure of the type of dye I use, a fiber-reactive dye. A fiber-reactive dye forms a covalent bond with the appropriate textile functionality, typically a cellulose fiber. I use 100% cotton. Now look at this example of an actual dye reacting with the cellulose, specifically the OH group. Since I used a fiber-reactive dye meant for cellulose, my strips of cotton were effectively dyed, but the synthetic thread on the edges remained white. There are other types of dyes that would have no effect upon the cotton, but easily dye the synthetic thread. So the next time you plan on tie-dyeing or vat dyeing, make sure to check the labels on your fabric and dye of choice, otherwise it might not work. Also, as demonstrated by my dye experience, the dyes can weaken the fabric because of the way the dye molecules interact with the fiber molecules, so be careful of that. Good luck dyeing.